Hello, this is Dr. Baxley. Welcome to the third part of the Chapter 4 lecture video series. The main topic of this video lecture is going to be how ionic and molecular compounds interact with water in aqueous solutions. There won't be any calculations in this chapter, so you won't need your calculator. However, I always suggest that you have a copy of the printable lecture notes available so you can take notes while you're watching the video. This lecture picks up in section 4.5. It's all about aqueous solutions. The first thing discussed is electrolytic properties of substances when they dissolve in water. It turns out that water is actually a very poor conductor of electricity. It's one way to measure the purity of water. You just measure the conductivity. If it's really non-conductive, the water must be fairly pure. However, this doesn't allow you to take your toaster or your cell phone charger into the bathtub with you, because 120 volts of electricity is enough voltage to push electrons through the water and through you. Aqueous solutions of ions do conduct electricity pretty easily, though. There are three types of solutes that can be present in aqueous solutions. One type is called a strong electrolyte. In a strong electrolyte, the solute is all ions. Nothing is in a molecular or other form. Everything that dissolves, ions. A second type is a weak electrolyte. Weak electrolytes are soluble. They form some ions, but whatever is dissolving stays mostly intact as molecules. And then a non-electrolyte is something that dissolves in water, but doesn't make any ions whatsoever. The molecules stay intact as individual molecules when they dissociate from the solid and dissolve in water. Here's a figure from your book about how ionic substances dissolve in water. This particular substance could be shown as sodium chloride, or NaCl. And when NaCl solid dissolves in water, it turns into Na plus ions and Cl minus ions. When sodium chloride dissolves in water, the sodium and chloride ions separate from each other, and they exist as individual ions in the solution. For example, we can see that the chloride negative anion is surrounded by water molecules, and it's separate from the sodium cation that's also surrounded by different water molecules. The solid in the middle is shown as that three-dimensional network of ions, that repeating positive-negative charge combination we saw in the previous lecture video. But as it dissolves, the solid turns into separate ions, and they float away from the solid in water. These ions then move in response to electric current. That's what gives the impression of electricity being conducted through the water. It's really not electrons moving through the water, it's just the ions moving in response to the electric field. This figure shows a molecular substance dissolving in water. This particular substance is methanol, which is a very harmful alcohol to drink. When methanol molecules mix with water, they're surrounded by water molecules, just like the ions were, but they exist as individual discrete molecules, not as ionic substances. Would this be a strong electrolyte, weak electrolyte, or non-electrolyte? Since there are no ions, this must be a non-electrolyte. This figure shows two substances coming from the shakers into beakers of water. They're being tested by an electrolyte tester, where there's a light bulb hooked up to a battery, and there are two electric leads that go into the solutions. Your job is to figure out which substance is in each beaker. Is table salt in the beaker, or is table sugar in the beaker? Pause the video, think it over for a moment, and then we'll discuss the answer. The answer, of course, is that salt was in the beaker on the left, as the salt, or sodium chloride, dissolves in the water. It would form Na plus ions and Cl minus ions, and those ions would move in response to the electric field generated by the battery. The positive ions would move towards the negative electrode, and the negative ions would move towards the positive electrode. In the beaker on the right, since the light bulb does not light up, the substance must have been the sugar, table sugar, or sucrose, which is a molecular substance. And when it dissolves in water, it doesn't form any ions at all. Without any ions, the water is not a very good conductor of electricity. There are two ways that ions can form in water. One's called ionization, and one's called dissociation. The end result is the same. You still end up with ions in water, but they're two slightly distinct pathways in order to get there. First of all, dissociation is when an ionic substance dissociates, or the ions separate from one another. In sodium chloride, the sodium ions and chloride ions are already charged particles, and the water just serves to separate them from each other to go into solution. The second type of forming ions is called ionization, and that's when a molecular substance that doesn't exist as ions reacts with water, which is not an ionic substance, it's also molecular, and that combination forms new ions. An example of that would be HCl in the gas phase. While HCl you might think of as H plus and Cl minus, in the gas phase it's just a molecular substance, individual HCl molecules that are separate from each other. When HCl gas is bubbled into water, it forms the hydronium ion and a chloride ion. So there are new ions that are present where there didn't used to be ions at all. Here's more information about strong and weak electrolytes. Strong electrolytes exist nearly as 100% ions, and they're always either ionic compounds or strong acids. When they dissolve, they turn into ions. An example are all ionic compounds dissolving, such as the sodium chloride that turns into Na plus and Cl minus ions, like we've seen before. There are very, very few NaCl pairs of ions present, and so for this class we just assume that it's a 100% reaction from solid into ions. Strong acids are another category of electrolytes that are strong. Strong acids like HCl that we saw before, they exist nearly as 100% ions too, so this reaction also goes forward almost all the way to completion. Notice that in this particular equation, the H is written as H plus. Chemists are pretty lazy, and so we often write either H plus or the H3O plus, the hydronium ion that we saw before. Chemists will use these two formulas for what happens when acids react with water interchangeably. We'll use them both, and I know it might be a little bit confusing to students, but that's just the way chemists kind of are. Here's a list of the strong acids that you should know. I've got the names, you should be able to write the formulas. So take a moment, write down the names of these strong acids, and then write down the formulas for them because you knew or learned how to name acids way back in Chapter 3. Here are the formulas, I'll write them in for you, but you should have done these on your own. Sulfuric acid is the acid of sulfate, so that's H2SO4. Nitric acid is the acid of nitrate, so that's HNO3. Chloric acid is the acid of chlorate, so that's HClO3. Perchloric acid is the acid of perchlorate, that is HClO4. And then the hydrochloric, hydrobromic, and hydroiodic acids are all acids of the anions chloride, bromide, and iodide. In this last column of acids, is there an acid missing? Maybe an element that you think would make another acid? Absolutely. Notice that HF is not on this list. That's because HF is actually a weak acid. If you've seen Breaking Bad, in one of the seasons, they show Walt, the chemist, dissolving a particular object in hydrofluoric acid in a bathtub. And the whole bathtub dissolves along with that object and craters down into the basement of the building. Turns out that HF, while fairly reactive with some substances like glass, won't dissolve that kind of object, and it won't dissolve a bathtub. It was a little bit of Hollywood mayhem that wasn't chemically accurate. Chemists have much better ways of dissolving bodies, by the way. Here's some more information about weak electrolytes. Weak electrolytes dissolve in water, and they only make a small percentage of ions when dissolved. Weak electrolytes are either weak bases or weak acids. When weak electrolytes dissolve, the ions of the weak acid that form with water are in equilibrium with the molecule that hasn't ionized. Weak electrolytes can be very, very soluble. They just don't ionize and make ions. Some common weak electrolytes are acetic acid, citric acid, ammonia that you might have for a cleaner, and some other amines that you might find around your house. Here's an example reaction of a weak electrolyte. This is where acetic acid, something you might find in vinegar, when it dissolves in water, it stays as 95% molecules, and only about 0.5% of the total number of molecules that get put into solution turn into H+ and acetate. Notice the stoichiometry of the reaction. For every 1 molecule of acetic acid, it will form 1 H+ ion and 1 acetate ion. Here's some helpful notes about compounds in solution. When you have polyatomic ions in an ionic compound, those polyatomic ions remain intact as ions when dissolving in water. Molecular compounds remain intact as molecules when they dissolve in water. They're non-electrolytes, they don't fall apart. Here are a couple of examples. Potassium phosphate, as a solid, would turn into 3 potassium ions and 1 phosphate ion as the solid potassium phosphate dissolves in water. Another example might be nitric acid. As nitric acid dissolves in water, being a strong acid, it would turn into H+ and NO3-, and those are both aqueous. Notice that both of these polyatomic ions stayed intact. They didn't fall apart into phosphorus and oxygen or nitrogen and oxygen. This next slide is for information about a picture of a strong acid, and it's a much more interactive part of today's lecture video. In this particular picture, we're working with a strong acid, HA, where A just stands for an anion of a strong acid. So you could take your pick of your favorite strong acid anion. My favorite's nitrate. So we could think of this as nitric acid. In this case, that strong acid is going to be ionizing with water to make H3O+ and A-. On the left side of the slide, there is a bar chart for number of moles of HA. And we'll just assume there's 10 moles to start with. In the center of the slide, there's an empty space. In the empty space, after you pause the video, I would like you to fill in the bar charts relative to each other for the substances HA, H3O+, and A- after the HA molecules ionize with water. On the far right side of the picture, I would like you to draw a mental model style diagram of what a strong acid looks like in solution. So that would have the relative number of molecules of HA, H3O+, and A- present in solution. You can ignore the water in the mental model if you'd like. So pause the video, fill in the bar chart, fill in the picture of the strong acid, mental model style, and then resume the video to see what the answers are like. Okay, thanks for drawing the picture. Remember, a strong acid ionizes to 100% completion. And so if we have 10 moles of HA present, based on the stoichiometry of the reaction, there would be a 1-to-1 ratio with H3O+. There would be 10 moles of H3O+, and there would also be 10 moles of A-, since it's a 1-to-1-to-1 mole ratio. Now the bar chart would end up looking like this, where the H3O+ and the A- are equal to each other, and they're also equal to the initial number of moles of HA, 10 moles. And the HA is decreased to 0 because that reaction is a 100% reaction. Now I know this may throw some people off, considering that they might think that 10 would go to 5 and 5. But look over in the picture box, and let's look at the blue pens as a representative of a strong acid, where each strong acid is composed of an anion, the pen base, and an H+ ion, the pen cap. In a strong acid, the ionization is 100%, meaning all the H+'s come off to react with water. So starting with 4 pens plus caps, meaning the acid molecule, when that ionizes, it forms 4 pens and 4 pen caps that are separate from each other. We started with 4, we ended with 4 of each of the products. Yes, there's 8 total things, but that's because the one thing split in half. Let's look at the picture, mental model style, of what the strong acid would look like in solution. A strong acid in solution is going to have no HA particles left over, and everything would be H+ or H3O+ and A-. So one can see here in the middle there's an H3O+ ion, and then there's an A- ion. And that's true for all of the acid particles. They're all in the form of H3O+, and there's no HA present anywhere in the diagram. Next up is the same sort of activity with a weak acid. We have a weak acid, again where HA stands for the formula of any generic weak acid. You could pick your favorite anion of a weak acid. An easy one would be HF. And the weak acid is going to ionize with water to form H3O+ and A-. Again, we start with the bar chart of the relative number of moles of weak acid. So we could assume that was 10 moles again. You'll be filling in the bar chart in the middle, and you'll be filling in the picture of the weak acid mental model style for what it would look like when the HA reacted with water to form the hydronium and A- ions. So pause the video, fill in the bar chart and the mental model, and then pick the video back up, and we'll see what the answers are. All right, in this particular case, this is a weak acid. So remember, weak acids don't ionize to 100%. They might ionize to 1% in solution, meaning that most of the HA stays together as a molecule, and only a few H3O+ and A- ions will form. Here's what the bar chart would look like then. Mostly HA particles, and only a small number of H3O+ and A- particles that would be the same relative heights on the bar chart. We can look at the same kind of demonstration with weak acid instead of a strong acid, where the green pens are the weak acid, and the pens are again H+ ions, and the pen bodies are the anion. Weak acids are green, of course, that's why I switched pen colors. So in a weak acid, not all of the acid particles are going to ionize. Maybe only one of the acid particles would ionize. The rest of the pens stay in solution as molecules, not as ions. The mental model picture would look like this, where most of the acid particles stay intact as HA particles, or neutral molecules, and only a small number of H3O+ particles form, and a small number of A- ions form. But most of the acid is dissolved in water and stays in the form of HA. The next part of the lecture video discusses precipitation reactions. Precipitation reactions are reactions that form solids or precipitates from ions in solution. A particular type of precipitation reaction is called a double replacement reaction, and this is where cations switch places with anions to form two new ionic compounds. A precipitation reaction is a special kind of double replacement reaction. They're also called exchange or metathesis reactions, so we can have 4 different names for one type of reaction. In precipitation reactions, the solid precipitate forms. And a question a lot of students have is, how do we know what the precipitate will be? Well, a chemist could go into the lab, and the chemist could be in the lab and mix a bunch of chemicals together. and use some qualitative determinations to find out what the precipitates are. That takes a lot of work, and you have to be in lab. Another way to figure out what the precipitates would be in a particular mixture of ionic compounds would be to consult a table of rules or guidelines for what kind of compounds are soluble in water. There just happens to be such a table in your text. Table 4.1 in your text has different solubility rules. Let's walk through the solubility rule table to find out how we can use it to determine if something's going to be soluble or not. The top half of the table has compounds that are generally soluble. There's a specific rule that most of the group 1 elements, the lithium, sodium, potassium, rubidium, and cesium too, but chemists don't use those very much, that those ions typically make compounds that are soluble. Ammonium is another one. It gets lumped in this group because it's a +1. So the group 1 on the periodic table plus ammonium, those compounds are typically soluble with no important exceptions. So if you ever see a sodium compound or a potassium compound, you know it's going to be soluble in water. Another group of ions with no exceptions to their solubility are the nitrate and acetate ions. If you see some crazy transition metal like iridium or ruthenium, and it has a nitrate or acetate anion, you know that compound is going to be soluble. And there are also no important exceptions. Chlorides, bromides, and iodides are almost all soluble, except for a few particular cases. The lead 2+ and the silver plus are fairly common examples of insoluble chloride, bromides, or iodides. Mercury is on the list also. This is actually the Hg1 or mercury 1 type of compound. Chemists don't use mercury a whole lot because it happens to be a neurotoxin. You won't see that in the chemistry lab this semester. So, mostly, the chlorides, bromides, and iodides are soluble, with a few exceptions, primarily the silver and the lead 2. Another compound that's usually soluble would be a sulfate compound. They have some group 2 exceptions, the strontium and barium, the larger ions in that group, and then a couple other ions, lead 2+ and silver plus. The calcium sulfate is kind of on the borderline. It's right in the middle of being soluble or insoluble. The bottom part of the table are compounds that are typically insoluble. So hydroxides and sulfides are typically insoluble. However, this set of rules is hierarchical, meaning that the group 1 from the periodic table and the ammonium cation compounds are still soluble. That rule takes preference. So sodium hydroxide, soluble. Other compounds containing those ions, not soluble. Hydroxide's got a couple of important exceptions to that rule, namely some of the group 2 ions that are a little bit bigger. Magnesium hydroxide, however, is pretty much insoluble. Carbonates and phosphates, usually insoluble. Now, that's a lot of stuff to remember, and I don't expect students to actually memorize this entire table of solubility rules. It's helpful to know some general guidelines, but knowing a lot of things isn't super useful, and I'm not big on memorization. However, knowing these solubility rules will make you more efficient at solving problems in the chemistry class. So these are the ones you should know. First of all, when we talk about soluble, we have to have some kind of definition. So the definition of soluble means that 0.01 moles of the substance dissolve in a liter of solution. So here's a rule to remember. The nitrates, the acetates, the ammonium ion, and the group 1 salts, those are all soluble. So that kind of lumps a lot of things into one general rule. Next rule is that the chlorides, bromides, and iodides are usually soluble, except for those 2 exceptions. It's kind of nice to have this rule because chlorides especially are very common in the chemistry lab. Another rule to remember is that hydroxides are almost all insoluble, except for this first rule, and then 3 exceptions of calcium ions, strontium ions, and barium ions. Those are just the 3 to remember, It's not so bad. It'll make you a lot more efficient at solving chemistry problems, so you should be familiar with these for quizzes or exams. So know those. A helpful rule is that sulfates are mostly soluble. It's helpful to know this because sulfates are very common in a chemistry lab. Another rule that's helpful to remember is that phosphates and carbonates are mostly insoluble, again, except for that special rule number 1, which was the group 1 salts and ammonium cation salts. Let's take a quick peek at the solubility rules. Which of the following compounds would expected to be soluble in water? You should pause the video and flip back and forth between these compounds and the solubility rules and make a note as to which ones are soluble and which ones are insoluble. So pause the video, come back, and check out the answers. Looking at the solubility rules, we know that all sodium compounds are soluble and all nitrate compounds are soluble, so sodium nitrate is definitely soluble. Oh, also note that soluble doesn't get spelled with an A like valuable. Common misspelling in chemistry class. Barium hydroxide. Now, while hydroxides are usually insoluble, barium is one of the exceptions, so barium hydroxide is soluble. Iron 3 hydroxide, since hydroxides are usually insoluble and iron isn't one of those exceptions, this would be insoluble. Ammonium sulfide. Ammonium is one of those special group 1 kind of cases. This would be soluble. Lithium sulfate, because of lithium being always soluble, that's soluble. Lead 2 bromide, that's one of the exceptions to bromide, so that's insoluble. And mercury nitrate, mercury 2 nitrate. Well, all nitrates are soluble, so this one is definitely soluble. We can use those solubility rules to predict the products of different chemical reactions. For example, what chemical reaction might happen when solutions of potassium iodide and lead 2 nitrate are mixed? Here's a chemical equation that describes the reactants forming products. This is a double replacement reaction, so the negatively charged nitrates switch places with the negatively charged iodides, and the products are the lead 2 iodide and the potassium nitrate. So one might want to know, what are the states of matter of the lead 2 iodide and of the potassium nitrate? Again, you can go back to the solubility rules and figure that out. Here's a pretty picture of what the reaction looks like. It makes a beautiful solid of lead 2 iodide. Once you look back at the solubility rules, you'll notice that all potassium compounds are soluble and all nitrate compounds are soluble. So this one's double extra soluble. We can see from the chemical reaction that there's a solid that forms. The solid must be then the lead 2 iodide. Here's a mental model style picture of what's happening when the potassium iodide solution mixes with the lead 2 nitrate solution. In this particular mental model, there's some nice features. One can see clearly that the numbers of iodides and potassium ions are 1-to-1, just like in Ki, and the numbers of nitrates to lead 2 ions are 2-to-1, just like in the chemical formula. One can also see that there are 2 lead 2 plus ions in solution, and there are 5 iodide ions in solution. We'll see if that ratio of the 5 iodides to the 2 lead ions continues on through the rest of this picture. The next picture shows a beaker of the different ions being mixed together. So this is before a reaction happens, but everything is mixed. The next picture over shows what happens after everything is mixed together. There's some nitrate ions left over. There's some potassium ions left over, and they're separate from each other in aqueous solution. And at the bottom of the beaker, there's some lead 2 iodide solid, and you can see clearly from the drawing that there are a lot of lead ions. 1, 2, 3, 4, 5 lead ions, and there are 5 iodide ions. That is not a very good representation of what lead to iodide would look like. If this author turned in this mental model for a lab report, for example, it would not earn full credit. A better picture would show 2 lead 2 iodides as solids, plus an extra iodide ion left over. The next section of the text talks about something called net ionic equations. Net ionic equations are kind of useful because they show you just what's happening, and they kind of ignore some of the ions that aren't really participating in the reaction much. So here's some steps for writing net ionic equations. First of all, write the balanced chemical equation, just like you would before. We'll call this a complete equation because it's got every substance present in it. Next, write a chemical equation that dissociates or ionizes any and only the strong electrolytes, so anything ionic and soluble, and then the other category of strong electrolytes, the strong acids. The next step is to cross out spectators. Spectators are ions that are on both sides of the reaction arrow, but that don't really change from one side to the other. What's left is the net ionic equation. The box here below, at the bottom of the slide, tells you what kinds of things don't make ions. For example, molecular substances. They don't make ions. Things like the methanol that we saw on a previous slide, or the sucrose we saw on a previous slide. Water is a molecular substance. It doesn't make very many ions in solution. Mostly molecules keep it together as a molecule. The weak electrolytes, like HF, they don't ionize much, only to 1% or so, so we keep the HF molecules together. Solids or precipitates don't turn into ions because they're not soluble. And then gases that form in a chemical reaction, like H2 or CO2, get treated as molecular compounds that would be separate from the aqueous solution. They're bubbling away from the solution. They're not going to turn into ions. So everything in that last box, keep together. They don't exist as ions in solution. Let's do an example of a net ionic equation for a reaction between barium hydroxide and HCl, both in aqueous solution. First we'll write a balanced chemical equation, including states of matter. Then we'll write the total ionic equation, and then the net ionic equation as a result from crossing out spectators. Think for a moment what the products of the reaction might be. It's just a simple double replacement reaction, so we can begin by writing the barium hydroxide, combining with the HCl. And those will react to form in a double replacement reaction, barium chloride. And we can tell from the solubility rules that this would be aqueous. And the other product would be H2O. H2O would be considered liquid, even though there's some water present in the solution. We need to balance the equation. There are 2 chlorides in the products. There need to be 2 chlorides in the reactants. And so now there are 4 total hydrogens in the reactants. We will need 4 total hydrogens in the products. The next step is to write the total ionic equation, or writing the equation to show that everything that's going to exist as ions is as ions. So barium hydroxide, being soluble and ionic, would end up being barium 2+, and 2 hydroxide ions in solution. HCl is a strong acid, so that will be 2 H+ ions, plus 2 Cl- ions. The barium chloride is aqueous because it's soluble, so it's another barium ion, and 2 chloride ions. And the H2O is a molecular substance. It stays intact as H2O liquid. Now I've left off the states of matter for all the other substances. That's okay. The total ionic equations get pretty crazy if you include all of the aqueous substances. I do suggest, however, anything that's not aqueous, a liquid, a solid, or a gas, that you go ahead and note what the state of that matter is, so you don't confuse it with ionic things. The equation can now be evaluated for spectator ions. Looking at the equation, barium ions are the same in both the reactants and the products. So are chloride ions. They don't change. So these ions are considered spectator ions. The spectator ions can be canceled out, and what's left will be the net ionic equation. In this case, that works out to be 2OH minus plus 2H plus, and that turns into 2H2O liquid. Since we're dealing with a net ionic equation at this point, the states of matter of the reactant should be included. And so this would be the total ionic, or net ionic equation, sorry. This would be the net ionic equation. Since this net ionic equation isn't balanced exactly the way we'd like an equation to be balanced, because the coefficients are all 2, this could be rewritten as OH minus plus H plus goes to H2O. So this would be the most correct form of the net ionic equation. Here's another example of a net ionic equation. In this case, you'll be writing the complete total ionic and net ionic equations for when aqueous solutions of silver nitrate and nickel chloride are mixed. If you recall, silver is always a +1 and nickel is always a 2+. So that will help with writing formulas. Go ahead and give this whole set of equations a try. The total complete equation, the total ionic equation, and net ionic equations, and resume the video and see what the answers are. For the complete equation, we start with the silver nitrate in aqueous solution. That will react with the nickel chloride, also in aqueous solution. That will form the nickel nitrate plus silver chloride. A quick check of the solubility rules reminds us that all nitrate compounds are soluble, so the nickel nitrate will be aqueous. And chloride compounds, while usually soluble, chlorides are not soluble with silver. It's one of the exceptions. So this would be not aqueous, but solid as a precipitate. This equation needs to be balanced. There are 2 nitrates in the products, so there need to be 2 nitrates in the reactants. There are now 2 silver ions in the reactants. There need to be 2 silvers in the products, so the coefficients of 2 will balance the equation. For the total ionic equation, everything in the reactant side will be in ions. 2 Ag plus, 2 nitrates, 1 nickel 2 plus, 2 chlorides. That'll form a nickel 2 plus, 2 nitrates, and the silver chloride, since it's a solid, would stay together as 2 AgCl. Looking at the equation, the spectator ions are going to be nickel and nitrate. So the net ionic equation is going to end up being Ag plus aqueous plus chloride ions aqueous go to form silver chloride as a solid. I've left out the coefficients of 2 for each of those elements because I could readily see that the coefficients of 2 could be reduced and replaced with 1s to show the net ionic equation here at the end. Here's another example for you, an aqueous solution of potassium phosphate mixed with an aqueous solution of iron 2 nitrate forming a precipitate. Go ahead and give this one a try. Go see your instructor if you need some help with the answer. Here's a quick concept check. Which substance has the largest number of ions form when dissolved in aqueous solution? Check out the 3 compounds, take your vote, and resume the video to find out what the answer is. In this particular case, the number of ions that would form when sodium acetate dissolves in water would be 2. There'd be a sodium ion and an acetate ion. Why only one ion for acetate? Because you remember from earlier in this video that polyatomic ions stay intact when they dissolve in water from ionic compounds. For the second option, potassium carbonate would turn into 2 K+ ions and 1 carbonate ion. In the third example, the sodium phosphate would turn into 3 sodium ions and 1 phosphate ion. So the total number of ions would be 2, 3, and 4, meaning that the sodium phosphate turns into the most ions. Here's another concept check. Of the 5 substances listed below, classify each one as strong electrolyte, weak electrolyte, or non-electrolyte. Pause the video and then resume to figure out what the answers are. Sodium chloride, it's a soluble ionic compound, so this is going to be a strong electrolyte. Ammonium carbonate, ammonium compounds are soluble, this is also going to be a strong electrolyte. Sucrose, we saw that way back with the electrolyte tester. Sucrose is a molecular compound, it's going to be a non-electrolyte. HF is one of the weak acids. It's not one of the 7 strong acids you're supposed to memorize, so HF is going to be a weak electrolyte. Methanol is another one of those non-electrolyte compounds, being molecular, so that's non-electrolyte. That's the end of part 3 of chapter 4 lecture video. Hope you found it useful, and as always, if you have any feedback, I'd love to hear it. Whether it's good feedback or not so good feedback, let me know so I can improve these lecture videos for you.